Okay, today we're going to be talking about the fundamental theorem of calculus part 2, and we're going to begin by trying to discover or prove what this theorem actually is. And so if you notice here in part A, we have the derivative of an integral from a constant 1 up to the letter x of some function t squared dt. So what we're going to do is we're going to work from the inside out. We're going to integrate this function t squared by using the power rule. So that's going to give us t cubed over 3. We've already integrated, so we'll make a straight line. We're going to plug in our upper limit, and we're going to get x cubed over 3 minus our lower limit of 1/3. Now we're going to go to the outside, and we're going to take the derivative of this function with respect to x. And we'll notice something very interesting will happen. If we take the derivative of x cubed over 3, we get back to simply x squared. If we take the derivative of this constant, it goes away because it's 0. And we do all of that work to end up getting back to x squared. Interesting. Started with t squared over here. Let's see if it works the same way if we go from 5 to x as opposed to going from 1 to x. I'm going to integrate again, and I get t cubed over 3. And I'm going to make a straight line. I'm going to plug in my upper limit of x cubed minus, I'm going to plug in my lower limit of 5 cubed. That's going to be 125 over 3. And then I'm going to take the derivative right back. And I take the derivative of the term with respect to x, I get x squared. The derivative of the constant is 0. So, my friends, we have just proven the fundamental theorem of calculus part 2, which is if you take the derivative of an integral from any constant, it doesn't matter what the constant is, to the x of any function, you end up getting this function with the x plugged in. Notice we got x squared. This works because no matter what this number is, no matter what this number is, when you take the derivative of it, it's a constant, it's going to always be 0, and you're only going to get that value. So, for part C and D, we can go ahead and skip past this, and we don't have to work it all out anymore because we have the theorem. The derivative of this integral of pi over 6 to x of cosine of t is simply cosine of x. All right, we notice in part D we have the exact same function. Instead, we're going from pi over 2 to x, but we just proved that this constant is irrelevant. So therefore, it's going to be, once again, cosine of x. So once again, here is our fundamental theorem of calculus part 2. You have the derivative of an integral from any constant a to x, f of t dt is equal to f of x. And if you're going from the letter x up to the constant a, we know that's just going to be the opposite, negative f of x. So let's apply that to example 2. Find capital F prime of x, the derivative of f of x. So we see that capital F of x is the integral from some constant, pi over 4, to x of t sine of t dt. We want to find capital F prime. So that means we need to take the derivative of both sides of this function. The derivative of capital F of x is capital F prime of x. Now we can apply the fundamental theorem of calculus part 2. The derivative from any constant to x of t sine of t dt is simply x sine of x. And that is the answer. It's pretty simple as far as understanding the theorem. Okay, and just like anything else, we have a chain rule version of the fundamental theorem of calculus part 2. If you're taking the derivative of a function f of t, but the limits are some function other than just the constant and something other than just x. So you have a function that has x's in it and another function that has x's in it. Then what you have to do is you have to plug in the upper limit into the function and then multiply by the derivative of what you plugged in. There's their chain rule. And then if the bottom is also a function of x, then you need to do the same with that. So let's go ahead and take the derivative of both sides of this function. And we have 3x squared and 5x as our limits, and the square root of 1 plus t squared dt. So the derivative of g of x is simply g prime of x But here, we need to apply the chain rule. So we're going to plug in 3x squared in here for t. We have to remember that t is being squared, so that's going to end up giving us the square root of 1 plus 9x to the fourth. And then we're going to multiply that times the derivative of the part we plugged in, which is 3x squared, so that's going to be 6x. Minus f of the bottom, so that's going to be, we're going to plug in 5x into our formula. So 1 plus 5x squared is going to be 25x squared. And then times the derivative of 5x, which is 5. So let's clean this up a little bit. It's going to be 6x times the square root of 1 plus 9x to the fourth minus 5 times the square root of 1 plus 25x squared. Okay, now we're going to put it all together and we're going to bring back some of the concepts that we have been studying all year. You have the graph of a function f consists of a circle, quarter circle, and line segment. So anytime you see the words quarter circle and line segments, more than likely you are going to have to use the concept of area of some sort in order to do this problem. All right, so you have g of x is equal to the integral from 0 to x f of t dt. And this is the graph of f. So we need to find g of 0. G of 0 means plug 0 in wherever we see an x. So g of 0 is simply going to be, so let's write it out, g of 0 is simply going to be the integral from 0 to 0 of f of t dt. Well, we know that anytime you integrate from a number to that same number, you don't get any area under the curve, so that's just going to be automatically 0. So that's an easy one. Okay, g of negative 1 means you're going to integrate from 0 to negative 1 f of t dt. Now notice the limits of integration are backwards, 0 to negative 1. So I'm going to go ahead and rewrite that with a negative, and I'm going to go from negative 1 to 0 of f of t dt. Now if I go from negative 1 to 0, I notice that this is a triangle that has a base of 1 and a height of 2. So remember that it's going to be base times height divided by 2. So 1 times 2 is 2, divided by 2 is 1. And so that's going to be 1, but there's a negative in front of that, so it's going to be negative 1. All right, and now let's go ahead and do the same with g of 2. G of 2 means to integrate from 0 to 2, so we'll go ahead and write that out. G of 2 is equal to 0 to 2 f of t dt. All right, so now we're going to go from 0 to 2. We notice that this is a quarter circle, so this is going to be our pi r squared divided by 4. Our r is 2, so 2 squared is 4 over 4. That is going to be pi. Looks like an 11. And then g of 5. So g of 5 is going to be the integral from 0 to 5 of f of t dt. Okay, so we've already figured out that 0 to 2 is going to give us pi. So we'll go ahead and write that down. Pi plus whatever we get from 2 to 5. So everything here is underneath the x-axis, so it's going to be a negative numbers, but let's go ahead and figure that out. So from 2 to 3, we have a triangle, which is going to give us an area of negative 1 because it's underneath the, or area of 1, but it's underneath, so it's going to be negative. And then each one of these boxes is going to be an area of 1, so that's going to be plus 1 for this box, plus 1 for that box. And then we have another triangle right here, so that's going to be a base of 2, height of 1, so that's going to be another negative 1 there. Actually, I need to make these negative as well because they are, everything's underneath the x-axis. So let me just go back and do that. It's going to be negative 1, negative 1, negative 1. So when you put it all together, g of 5 is going to end up being pi minus 4. All right, it says on what intervals is the graph of g increasing? Now this is when we have to go back and remember some things from our derivative portion of the course. So what we want to do is we want to take the derivative of both sides. We know that a function g is increasing, let's interpret that, when its derivative, g prime, is positive. So we're going to take the derivative of both sides. So g prime of x is equal to the derivative of an integral from 0 to x of f of t dt. The derivative of any integral from a constant to x of f of t is f of x. That's your fundamental theorem of calculus part 2. So we have just made a very important connection that we have to use for the rest of this problem, and that is the fact that g prime of x is really f of x. So right over here, we will say this is really the graph of f and g prime of x. So where is g prime of x positive? Well, it's going to be positive everywhere it's above the x-axis. So that's going to be from -1 to 2. All right. Find all values of x on the open interval from -1 to 5 at which g has a relative maximum. So let's review that. Relative maximums occur when the derivative of a function changes from positive to negative, because that means the original function is increasing and then decreasing, which gives you a maximum right there. So when does this function change from positive values to negative values? That's going to be at 2. So at x equals 2. All right, letter D, find the absolute. Okay, so we need to underline that word. Absolute minimum value. Now, anytime we see an absolute, that means we need to use, it's back, the extreme value theorem. The extreme value theorem, let's review, says that extreme values occur at either the critical points or the end points. So, what are our end points? -1, so we need to find the y value of that. We need to find the y value at our other endpoint. And then we need to figure out what the critical point is. Well, the critical point is when a function's derivative equals 0 or when it is undefined. Well, remember, this graph is really g prime of x. So when does this function equal 0? Well, it equals 0 at x equals 2. So you have a critical point at x equals 2. So we need to find f of 2. Excuse me. All of these should be g's. So let me go back and fix all of this. This should be g. All right. So it's not going to let me do that. So let me just erase this here. These should all be g's. So this should be g of -1, g of 5, and then g of 2. So that's what we are looking for here. And our critical point is at 2. And our endpoints are, critical points occur when g prime of x is equal to 0. And this is our g prime of x. Okay? So g of -1, we already found that answer in part A. That was -1. And then g of 5, if you can remember, that was pi minus 4. And then g of 2 was pi. So we've already found all of these answers. And so now we're looking for the absolute minimum. The lowest one of these numbers is going to be this one, because 3.14 minus 4 is going to be, it's not going to be less than -1. So at g of -1 equals -1, that is going to be our absolute minimum value. Okay, part E. On what intervals is the graph of g concave up? So we know that a graph is concave up when its second derivative is greater than 0. All right, it's greater than 0. So remember, we have already made the key observation here that g prime of x is really f of x. Now we can take the derivative of both sides of this again and make another relationship. G double prime of x is equal to f prime of x. F prime of x, if we could maybe write it out, is the slope of f of x. So now basically we're asking the question, when is g double prime greater than 0? Or when is the slope of f of x positive? Well, that's going to be positive from -1 to 0. So -1 to 0 has positive slope. Then we have negative slope, and then we have positive slope from 3 to 5. So in union with 3 to 5. Now we want to look for the x-coordinate of each point of inflection. A point of inflection occurs when g double prime of x changes signs. All right, so in other words, when does the slope change signs? Well, it goes from increasing to decreasing when x is 0. It's decreasing, and then when 3, we see that it changes signs again. Part G of this long problem here, we want to write the equation of the tangent line when x is 3. So we remember that if we're going to write the tangent line, we're going to use the point slope formula. And so that means that we need a point and we need the slope. So we need f of 3, or excuse me, I keep saying f. We need g of 3 and we need g prime of 3. Well, g of 3 is going to be obtained by using this formula here, 0 to 3. So we're going to integrate from 0 to 3. We hadn't done that earlier. And so we need to do that now, g of 3. So therefore, that's going to be, if you remember, that's going to be 1. All right, and so that's going to be area of 1. Well, actually, no, I'm sorry. We're going from 0 to 3. So, excuse me, so that's going to be your pi. And then that's going to give you -1 from there, from between 2 and 3. So that's going to be my g of 3, pi minus 1. Now remember, this graph of f is really g prime of x. So to get g prime of 3, that is really f of 3. So we'll go 1, 2, 3, and we'll go down, and -2 is our slope. So y minus my y coordinate of pi minus 1, and that's going to be equal to my slope of -2 times x minus my x coordinate of 3, and we can leave our answer in point slope form. Example 5 should be a quick problem considering the last one we did. Given f of x is equal to this function here, which is a function that's defined as an integral. So what values of x is the graph decreasing? So we know that the function f is decreasing when its derivative, f prime of x, is negative. So we're going to take the derivative of both sides. So on the left side, we get f prime of x. On the right, if you remember, you're going to take the derivative of any constant to the letter x, is going to just replace all these t's with x's. So it's going to be x plus 2 and x minus 3 squared. Now look, there's our derivative right there. Now, in order to find our critical points occur when a function's derivative equals 0 or undefined. It's going to be equal to 0 when x is -2 and when x is 3. So we're going to go ahead and make our number line just like we did before. And we're going to put -2 here and 3 there. So now we're going to plug in a number bigger than 3 into our derivative. That's going to clearly give us a positive number. Now we're going to use our understanding of the multiplicity of roots. Well, at 3, you go to x minus 3. That is raised to an even power. If it's an even power, the signs stay the same. So that's going to be a plus over here. So plus, plus. Okay, it's the idea of bouncing. All right, and then -2. So x plus 2 is raised to the first. That's an odd number. The signs are going to switch. Okay, so when is it decreasing? It's decreasing from -infinity to -2. That's when the function's derivative is negative. Okay, example 6, suppose that 3x squared minus 12 is equal to the integral from c to x f of t dt. What is f of x? Well, this is a pretty simple problem. Remember, to get f of x, we would want to take the derivative of, tell you what, let's write it out here. We're going to take the derivative of the left side, and we're going to take the derivative of the right side. And so the derivative of the right side is just going to give us f of x because of the fundamental theorem of calculus part 2. The derivative of the left side is just going to be 6x. So that's pretty simple. F of x is 6x. All right. So now it says part B, find the value of c. So now we know f of x is 6x. So that means f of t is 6t. That's common sense. So we're going to plug in 6t right here. So we have 3x squared minus 12 is equal to the integral from c to x of 6t dt. So we're going to integrate. We're actually going to integrate this 6t, which is going to give us a straight line because we've already integrated. So that's going to be 3t squared. And then we're going to plug in our upper limit of x. So that's going to be 3x squared minus our lower limit of c, 3c squared. And that is all, remember, equal to 3x squared minus 12. So let me write that over here. 3x squared minus 12 is equal to 3x squared minus 3c squared. And then if we notice here, these are going to cancel out, leaving us with negative 12 is equal to negative 3c squared. Divide by 3, you get c squared equals 4. So c is going to equal to plus or minus 2. And now we have this last problem. It happens to be a particle motion problem. And it says here that the position at time t of a particle moving along the coordinate axis is s is equal to 0 to t f of x dx meters. So to get the position of the particle at any time, this is the formula that you have to use. Use the graph to answer the questions. Give reasons for your answers. What is the particle's velocity at time t equals 3? So now, there's an important connection that we have to make for every one of these problems. If you go back here, this is s equals this. So we're going to take the derivative of the left side, which is going to make that s prime of t. And then the derivative of the right side is simply going to be f of t. But what is s prime of t? We know that the derivative of the position is the velocity. So we've just made the important connection for the entire problem, that v of t is really f of t. So this graph, which is f of x or f of t, this is really the velocity graph. So what is the particle's velocity at time t equals 3? Hey, there it is. That is going to be, the velocity at 3 is going to be 0. Is the acceleration of the particle at time t equals 3 positive or negative? Well, we know the acceleration is the derivative of the velocity, or the slope of the velocity. So the slope at 3 is positive, so therefore basically the a of 3 is going to be a positive number. Part C, what is the particle's position at time t equals 3? To get the position, we use this formula here. So s of 3 is equal to the integral of 0 to 3 of f of x dx. So now we go to our function and we integrate from 0 to 3. Well, that's going to be a triangle, has a base of 3, so let's write that out, and a height of 6 divided by 2. 3 times 6 is 18 over 2 is 9. It's underneath the x-axis, so we have to make our integral negative 9. So when time is 3, this particle is left of the origin. Okay? When does the particle pass through the origin? Pass through the origin when its position is equal to 0. But notice the position function is the integral from 0 to a certain number or time. So when would the integral be 0? Well, that would be when the area underneath the curve cancels out with the area above the curve. So when t is 6, the area under the curve and the area above the curve will be 0. So if I integrated from 0 to 6, then I would get a area of 0, which is the position. Okay, approximately when is acceleration 0? Well, don't forget, we made this connection earlier that this graph, f of t, is really v of t. So, to take the derivative of both sides, f prime of t is really the derivative of vt, which is a of t, the acceleration. So when is acceleration 0? It would be when the slope of this function is 0. So that would be at t equals 7. Okay, part F is somewhat of a tricky problem here. When is the particle moving toward the origin and when is it moving away from the origin? Okay, so let's remember, if we plug in 0 for time, the position of the particle at time 0 means we integrate from 0 to 0, which is 0. So we know that at time 0, this particle, I'm going to use gold here, this particle is at the origin. Okay? Now, remember, the key connection that we made in this problem is that f of t is really v of t. So, between time 0 to 3, the velocity is underneath the x-axis, so that means it's moving left. So it's moving left for a while, for 3 seconds. But then, from 3 to 6, the velocity is above the x-axis, so that means it moves to the right. And remember, we already established at 6 seconds, it's going to be back to a position of 0. And then from 6 to 9, the velocity is still above the x-axis, so it's going to be going right again. So when is it moving away from the origin? It's moving away from the origin between 0 and 3 seconds. So we'll say away, 0 and 3, in union with, it's also going away between 6 and 9 seconds. And then it's going towards the origin between 3 and 6. So we'll say towards between 3 and 6. Okay, on which side of the origin does the particle lie at t equals 9? All right, so we can find the position at t equals 9 is going to be the integral from 0 to 9 of f of x dx. All right, so now notice here that if we integrate this, we're going to have some negative area, and then from 3 to 6 we're going to have positive area. That's going to cancel out. And so then from 6 to 9, that's going to give us a positive area. So therefore the position at 9 is going to be some positive number. Don't know what it is because we don't know what this function is and we don't know how to find the area underneath it. But it's going to be some positive number, which means that this particle is going to be on the right side of the origin.